Good evening, guys. Welcome you all. Very good evening to all of you. Welcome you all. So, how you are doing, everybody? You are doing great and all. Good evening to all of you. Welcome you guys. Welcome you all. I think we're in live. Check for this audio video, all of you. Is my audio video is clear to all of you? Tell me and do comment if the audio video is clear and comment it. Good evening, all of you. Welcome you guys. Welcome you all. So first of all, do comment the comment section whether the audio video is clear, high or not. Is the audio video is clear to all of you? Fine. So let's continue. Let's start our discussions, everybody. Let's start our discussions, all of you, everybody. Now, and we have a great announcement from Unacademy. So we are conducting the All India mock test. We are conducting the All India mock test. These are the dates you can note down here. So we can enroll for this All India mock test by using a code of B V Reddy, and with this you can have a real GATE experience, and you will get to know where you are standing and where you are committing your mistakes, and you will get to know here. And the top educators will take the classes, and you will get to know clear picture. So where you stand, what is your all India rank in these many days, right? And you can plan this Unacademy subscription with a no cost EMI, and the digital notes are available. You can access the digital notes PDF form. Hard copies not available, soft copies you can access it. And these are the new batches we are starting for ECE and electrical, ECE and electrical. You can access these classes, right? And these are the features of Unacademy Plus. The Plus students will get the top educators will take the classes and digital notes and test series, and the iconic students will get additional benefits of customized doubt solving features, printed notes, hard copies available. Iconic students, one-to-one mentorship, strategy and study program, and interactive open house sessions. Chalo, let's continue our discussions. And so last class we have discussed about the electric field, and we have discussed the चार्ज डिस्ट्रीब्यूशन हमने डिस्कस किया, गॉस लॉ डिस्कस्ड, एंड मैक्सवेल फर्स्ट इक्वेशन वी हैव डिस्कस्ड, राइट नाउ. And we have seen some problems on the Gauss law, and today's class will continue our discussions on the next topic, take down, that is work done. Take the topic of work done. So what is the work done here, tell me. Consider I have some electric field is like this. Consider we have some electric field is like this. This is my electric field. We have considered is a uniform electric field, and this uniform electric field, let us consider we have some charge is present inside the electric field. We have some charge is present inside the electric field. Now then the charge will experience some force due to this electric field. The force experienced by the charge, the force experienced by the charge due to the electric field, which is given as F is equal to Q into E. This is the force experienced by the cause of the electric field. So as a result, what happens now, the charge will get certain accelerations, and the charged particle will move along the direction of electric field. Now I want to I want to keep the charged particle at rest only. To keep the charged particle at rest, then what I need to do here? We need to apply equal amount of force in opposite direction. We should do now. This I am calling this as FA. This I am calling this as FA. Can you tell me now what is this FA is? This is the amount of force we need to supply to move the charged particle against to the electric field. That FA, which is given as what we can say here, that is Q into E. That is FA, which is given as Q into E, where FA is this is the force we need to supply against to the electric field to keep the charged particle stationary. All of you. Now, if I want to move the charged particle by a small displacement of dl against to the electric field, then how much this work to be done? This is work done. If I call this as a dw, work done, which is given as what I can say here, work done, which is given as a force into displacement. Force into displacement. Now tell me all of you. Work done, which is given as force into displacement. So to move the charged particle by a small displacement dw, which is given as what I can say now here, FA dot dl. FA dot dl. What is this FA is that is amount of need to do against to the electric field, isn't it? So from this what I can say, dw FA, which is given as QE dl. QE dot dl. So from this what is the work? You tell me. This is a small work. If I want the complete work, what I should do here? Then we need to do the integration, which I can as minus q, this line integration of what I can say here, E dot dl. Line integral of E dot dl. All of you, this is a work to be done to move the charged particle by a small displacement from the one point to the other point. If I want to move the charged particle from A to B, then how much this work to be done here? That is given as minus q integral of what I can say now here, A to B of E dot dl. A to B of E dot dl. This is the amount of work to be done to move the charged particle from A to B against to the electric field. Why this negative sign indicate? The negative sign indicate this is the work to be done against to the electric field. That negative sign indicates. All of you tell me this thing. So this is the W. Where what is the W is called as a, what is this W? This is the work done by the external agent. Where what is this W here? W, which is called as a work done by the external agent. What is this W is called as a work done by the external agent, right? And here if you see this thing here, if they ask you to find the work done by the electric field, that I am calling as WE. The work done by the electric field, which is given as Q into S integral of A to B of E dot dl. So this is where WE is called as a work done by the electric field. This is called as what? Work done by the electric field. In the problem, you need to see what work they ask you to find. Whether they ask you to find the work done by the electric field or work done by the external agent. Unless they don't mention, we can treat that as a work done by the external field only, external agent only. Done all of you? Next. As we have seen the work done by the external agent is given as minus q integral from a to b of what we can see this thing here, E dot dl. Now tell me now here, work done by the charge is given as, and so which is given as, what we'll get now here, this is called as a work done per unit charge is called as a potential difference. This we are calling it as VBA, which is given as, that is minus integration of a to b E dot dl, where this VBA, which is called as a potential difference, called as what? Potential difference. Potential difference. How this potential difference is defined as a, the potential difference between the 2 points, which is defined as what you tell me, VBA, that is given as work done by the charge. So from this you can see now the potential difference is defined as a work done by the charge, work done by the charge from moving from one point to another point against to the electric field. What field here? Against to the electric field. Work done by the charge moving from one point to another point against to the electric field. That is called as a potential difference. Now the potential difference, that is VBA, potential difference VBA, which is given as, tell me now here, minus integration of a to b E dot dl, E dot dl, that is VBA. Now I want to find the potential difference for the point charges. Now for the point charges, as we know electric field, what is the electric field? What is the electric field for the point charges, you tell me? E, which is given as kq by r square into ar cap. E is given as what I can say, kq by r square into ar cap. As we know dl, what dl is a differential length. So if you see carefully, now this electric field, which is in what system here? We have spherical system. So I can write the dl is also in a spherical system only, we can write. How we can write, to tell me now here, which is dr into ar cap plus r d theta into a theta plus what I can say now here, r sin theta d theta into, r sin theta d phi into a phi. Spherical system, remember now all of you how to write the dl value? Now Now if I replace this thing here in this formula, electric field and dl, so tell me what I'll get my VBA, potential difference, which is given as minus integration of A to B, which is given as KQ by R square into AR cap and dot with dl. Now dl dot is what I'll get, you tell me, dr into AR cap plus r d theta into A theta cap plus r sin theta d phi into A phi cap. Now if I take the dot product between these two, now you tell me now what I will get here, VBA, which I will get this thing as, tell me now here, minus K. So here what I will get now here, integral of distance of A I am calling it as RA, distance of B I am calling it as RB. What I will get now here, tell me, Q by R square into dr will come now, all of you. Next, yes, tell me now what I will get now, VBA, which is equal to, now this integration of this part, 1 by r square integration minus 1 by r. So what I will get now, minus or minus plus hoga, that is KQ by r. Limits we have RA to RB. Now tell me. So you can tell me now what is my VBA, which is given as KQ into what I can write now here, tell me, 1 by RB minus 1 by RA. Boliye all of you. 1 by RB minus 1 by RA. So this is my potential difference. This, which we can also write it as VBA, which is given as, I can say, I can write this thing as VB minus VA is equal to KQ by RB minus KQ by RA. And you can see now here where VA, which is given as KQ by RA, and VB, which is given as KQ by RB. These are the potential differences, where VA and VB, these are called as a absolute potentials. These are called as, what you tell me, VA, VB are called as a absolute potentials. VA, VB are called as a absolute potentials. All of you tell me this thing. So as we have seen previously, the potential difference के लिए we need the 2 points required, initial point and final point. But whereas in case of a potential के लिए the reference point is infinite, so which is given as integral from, that is from RA to RB. If I do from RA to RB, which will get this as E dot dl, this is called as a potential difference. And whereas potential means if the initial point is at infinite distance, then the potential difference is nothing but potential only, which is given as minus integral infinite to some finite point of E dot dl. This is called as a potential, or we can call it as absolute potential, or simply called as a potential. As a reference point is located infinite distance, the potential difference is nothing but potential only. All of you tell me. So that's why the potential V, which is given as, that is KQ by R. This is a potential. This is the potential. And potential is a what? Tell me scalar quantity. Potential is a scalar quantity. इसीलिए this is called as a electric scalar potential. This is called as a electric, and this is a scalar quantity. This is called as a electric scalar potential. All of you? Now if you see here carefully. Now, so here what is my VBA? Potential difference now. The potential difference which is given as what I can say here, minus integral of A to B of E dot dl. E dot dl. This is a potential difference between A and B. Now can you tell me what is my VAB? And where what is this VBA, which is given as VB minus VA, right? And tell me now VAB, which is given as minus integral of B to A of E dot dl. All of you tell me this thing. And which is given as VA minus VB. And this is given as VA minus VB. Now if I add these two here, equation 1, let us call this second equation. Adding the two equations, see what I will get now, tell me. Then VAB plus VBA, VAB plus VBA, which is equal to 0. VAB plus VBA, which is equal to 0. So from this what I can say now here, integral from what we can say now, A to B of E dot dl plus integral from B to A of E dot dl, which is equal to 0. Now tell me all of you, which is equal to 0. Everybody? Now if you see carefully, now I can write this thing as, now minus will be removed here. I can write this thing as integral from A to B of E dot dl, isn't it? Plus integral B to A of A dot dl, E dot dl, which is equal to 0. Now tell me all of you. अगर आपने ध्यान से देखा तो, if you observe carefully, where E, electric field intensity, is the vector quantity, electric field intensity which is a vector quantity, there by adding this thing, why it is plus here, I have written, you see this thing, what I have written here, VAB equal to minus VBA, VAB equal to minus VBA. If I add these two, will be 0 or not? So here try to understand what I want to present, right? Look at now here, integration of this my electric field intensity from A to B plus B to A, which is equal to 0, means what I did, you see carefully, we are finding the integration of one vector. Electric field is simply a vector quantity, मान लो. So integration of one vector from A to B and integration of one vector from B to A. So I did this thing here. That means integration of the vector from A to B plus integration of same vector from B to A I did. That means मैंने क्या किया, wherever we have started here, मैं वापस ये पॉइंट पर आया ना, सेम पॉइंट पर आया मैं घूम के. That means starting point, ending point is same now. So then what I should call this is now here? Then we can call this is nothing but closed path. So this is called as what we can say closed path we can call. Now tell me all of you. So that means I did one closed integral. So by combining this integral, I can write this thing as a closed line integration of E dot dl equal to 0. All of you देख के बोल this thing here. So I did one closed path I did. So this thing which I can call this as a closed line integration of E dot dl which is equal to 0. I can say closed line integration of E dot dl which is equal to 0. I can say boliye all of you. Right. So now you can see now here this is closed line integral of one vector is 0. So what I should write now here? So this means the closed line integration of E dot dl which is equal to 0. Here can we apply the Stokes theorem? Can we apply the Stokes theorem? Can I apply the Stokes theorem here? By using Stokes theorem, what we can do? We can convert the closed line integral to a open surface integral. That is open surface integration of what I can say now here? Del cross E dot ds which is equal to 0. Tell me. Open surface integral of del cross E dot ds which is equal to 0. I can say. From this which we can write this equation as what I can say now. Tell me. Del cross E which is equal to 0. Del cross C which is equal to 0. Now you can see now here what is this E here? Where here we are discussing about what type of fields here? Static fields, where this E is called as a static electric field. Where this E is called as what you tell me? Static electric field. So what you observed here, the curl of the static electric field is 0. If the curl of a static electric field is 0, if the curl of a vector is 0, then that vector is called as what you tell me? Irrotational or conservative. Irrotational or conservative. So from this what I can say now here? From this what we can say? Static electric field. What is the nature of a static electric field? What is the nature of the static electric field? Static electric field is what I can say is a what nature? Irrotational. Static electric field is a irrotational or conservative field. Static electric field is what we can say it is a irrotational or conservative field. Boliye all of you. Static electric field is what type of field is a irrotational or conservative field. Right. And so this equation which we'll call this as a this is called as a second Maxwell's equation, which is called as a second Maxwell's equation. This is called as a second Maxwell's equation for static field. What type of fields these are? Static field. Second Maxwell's equation for static fields. Right? Electric field is what type of fields are? Irrotational or conservative field. Done everybody? Now. Now as we have seen the potential V How we can write the potential? Tell me. Potential V, which is given as what I can say? Potential V, which is given as minus the line integral of what I can say now here? E dot dl. E dot dl. Now, so I am differentiating this equation both sides. If I differentiate now here, then I will get this thing as dV. All of you, if I differentiate now here, then I will get the dV, which is equal to minus E dot dl hoga na, tell me? E dot dl. If I say that dl is a vector, the differential length, if I call the dl which is along the x direction, let us say dx, if I say dx into ax, if I write, so then in that case what happens, you tell me now here? From this electric field E, which I will get this thing as minus of dv by dx hoga na. If I say differential length is along x direction, it will becomes minus of dv by dx. If it is y directions, then I will call this as x component. So if it is y direction, we can say ey, which I can write it as minus of dv by dy. And if it is z direction, then I can write this thing as ez is equal to minus of dv by dz. I can write. All of you tell me. I can write this thing as minus of dv by dz. Now if you see carefully, we have considered here where these are the differential length, these are the x component, y component, z components. So from this, can you tell me the component, all the components now here? Electric field, which we can write it as, it might have a x component, we can say ex into ax I can write, plus along y component is a ey into ay, plus along z component, which we can write it as ez into az I can write. So from this what I can write now here, this electric field E, which is given as x component is minus dv by dx into ax, y component is minus dv by dy into ay, and z component is minus dv by dz into az, right? So from this, the electric field E, which is given as minus of what I can write now here, the variation is along x direction, y direction, z direction. So this, which we can write it as what I can say now here, so which we can write it as del v I can write now here. Gradient operation I use since it is a three-dimensional parameter. Since it is a three-dimensional parameter, so we can see the variations along x direction, y direction and z directions. So E is equal to minus del V. E equal to what, you tell me? Minus del V. All of you boliye. So that means the electric field intensity, which is given as negative gradient of electric scalar potential. Electric field intensity, which is equal to negative gradient of electric scalar potential, where what is the E is the static electric field. E is what? Static electric field. And where what is the V is the electric scalar potential. Electric scalar potential. So from this, what I can say now here, the static electric field is what I can say? Static electric field is a negative gradient of electric scalar potential. All of you tell me. Where this negative sign, you can see now, this negative sign indicates that. What is the significance of this negative sign? Is a negative sign indicates that the direction of electric field is is along the decreasing direction of potential. The significance of this negative sign is what? The direction of electric field is along the decreasing direction of potential. Fine, all of you? Right. Yes. Now, अगर आपने ध्यान से ऑब्जर्व किया तो, and previously we have discussed the some, so after completion of vector calculus we have discussed one important point. If the curl of a vector is 0, then that vector is called as a irrotational. And there we have concluded one important thing here. All of you go to the note number 6. After completion of the vector calculus, before the static electric field, we have discussed the 1, 2, 3, 4, 5 and 6 notes we have discussed. And have a look at in the note number 6. For the note number 6, all of you go to the note number 6 and open that one and see that one. What is the note number 6 we have seen? You tell me. If the curl of a vector is 0, then that vector is called as a irrotational. And what we call now, any irrotational vector can be expressed as, any rotational vector can be expressed as gradient of some other scalar. अगर आपने ध्यान से देखा तो इधर you see this thing here. Look at now this curl of this E0, then E is called as a irrotational or conservative, we can say na. According to that property, since it is irrotational, what I can do? Any irrotational vector can be expressed as what? The gradient of some other scalar. Any irrotational vector can be expressed as gradient of some other scalar. All of you boliye. Any irrotational vector can be expressed as a gradient of some other scalar function. So this is one of the example of that statement. Is it fine, all of you? Done. Chalo. Next topic. Properties of isolated conductors under electrostatic equilibrium. Properties of isolated conductor under electrostatic equilibrium. Now see this thing. First of all, what is meant by electrostatic equilibrium means what? What is meant by electrostatic equilibrium means what now here? That means simple thing here, no movement of charges, means what we can say, no flow of charges. No flow of charges means the charges are at rest. No movement of charges, the charges are stationary or charges are at rest. First thing. Next, isolated conductor. What's the meaning of isolated conductor? That is a free conductor. Isolated conductor means without any energy. So that means free from energy sources. Isolated means what we can say now here, that is free from energy sources. Free from energy sources. Right. I think so previously, so here from the last classes onwards, starting onwards, I think some fellow is asking the question. I think some Madhu, I think so, some name, if I'm not wrong, some Madhu. So he is keep on used to ask the question. So this thing, so that question answer you can get here. If the Madhu, if you are here, and so here आज आपका the question का solution मिलेगा. Listen here. Properties of isolated conductor under electrostatic equilibrium means the first of all, equilibrium means what now? There is no movement of charges. Isolated means the charges are free from energy sources. Let us consider we have taken this is my some conductor. This conductor is kept like this. I am not supplied any sources for this conductor. That type of conductor is called as a isolated conductor. That type of conductor is called as a isolated conductor. Right. So here now let us consider here this is my some conductor we have taken. Right, this is my conductor. So this is a conductor. If we have given the energy sources, now here what is the isolated conductor means? For this conductor I don't apply any type of sources. There is no supply. No supply is there. What's happened? That we are going to discuss now. Is it fine all of you? Is it fine all of you? First of all you tell me. And if we see carefully, for this conductor, if we apply some energy, you see this thing, what is the basic understanding of the flow of current? You see, when we apply some potential, then see what happens now here. Because of this potential, so this one side, this is the positive charge will come, here it is a negative terminal will come. Inside we have charges are present. Inside we have positive charges as well as negative charges are present. Hana boliye. We have huge amount of positive and negative charges are available inside the conductor. Plenty of charges. When we apply the voltage now here, so we have the electric field is induced in this conductor. What is the direction of electric field? You tell me. The direction of electric field is from the positive to the negative. Electric field is along from where now? Always from positive to negative. This is the electric field direction. All of you. Now because of this electric field, the charges inside the conductor will experience a force. Force which is given as F is equal to what I can say now here, Q into E. F is given as what? Q into E. The force on the positive charges, if I say, which is given as plus QE. The force on the negative charges, which is given as what I can say, minus Q into E. So that means all the positive charges inside the conductor, will move along the direction of electric field, because of the force on positive charges is like this now, and all the negative charges inside the conductor, they will move opposite to the electric field. हाँ बोलिए, ये point clear हुआ सभी को? Positive charges will move along the direction of electric field and negative charges will move opposite to the electric field. As a result of this, then what's going to happen? You tell me. As a result of this, what happens now? The charge movement will take place inside a conductor. There is a flow of current inside a conductor. This is the working of a conductor. All of you, this is the flow for the flow. This is the condition. In this is the matter for the flow of current. Tell me all of you. Yes or no? Now you tell me this thing. So this is the basic scenario. Now what I did now, I have taken the same conductor but this conductor is kept isolated. Now for this conductor here, we apply the charges, energy we applied. Same conductor we have taken, but there is no energy for this conductor. For this conductor we didn't apply any energy, then what happened, you tell me? If we don't apply any energy to the conductor, you tell me what's going to happen. If I don't apply any energy to the conductor, you tell me what's going to happen, you tell me. Do we have any flow of current? Here we have flow of current is there now here. Now you tell me in this conductor, you tell me now here, do we have any flow of current in this conductor? अगर कोई करंट है क्या ये आइसोलेटेड कंडक्टर में? क्या देयर इज नो करंट, नो करंट. एंड अगर आपने ध्यान से देखो इधर, basically see here, when we apply the potential, we have electric field is developed. Because of the electric field, positive charges will move like this, negative charges will move opposite direction. Because of the movement of the charges, what happened, you tell me? Because of the movement of the charges, there is a flow of current. You tell me now, in this conductor do we have any flow of current? कोई करंट है क्या ना भैया? There is no current. There is no current means no flow of charges. No current means what? No flow of charges na here. If the charges are moving, we have a current. Hana boliye. See the statement now here. If the charges are moving means we have a current. But there is no current means what? Now charges are not moving. Charges are not moving means why the charges are not moving? Why the charges are not moving? So when the any particle will move, if we apply a force, then only the particle will move. When the any particle will move here, if we apply some force, the particle will move. Yes or no? Now you see this thing here. There is no flow of current means there is no flow of charges. Why there is no flow of charges? Because the force acting on the charges is zero. Because why the charges are not flowing? Why there is no movement of charges? Because there is no force acting. अगर फोर्स है तो चार्जेस से डिस्प्लेस होगा. हाँ ना बोलिए. अगर फोर्स है तो चार्जेस डिस्प्लेस होगा. But the charges are not displacement. No displacement means what you tell me now here? No flow of current. That means no flow of current means no force is acting on the charges. Force acting on the charges means in this case F is equal to 0. Basically F is given as Q into E. F is given as Q into E. हाँ ना बोलिए. Now अगर आपने ध्यान से देखा तो here, so QE equal to 0 means what? Now either Q0 or E0. Q into E0 means are both 0. If you see carefully inside the conductor, do we have charges present or not? Inside my conductor, do we have charges present or not? You tell me. Inside the conductor, Q is non-zero. If Q non-zero means what has to be 0? Q non-zero means what has to be 0? The only possibility is E must be 0 now. What is this E is? What is this E is? This is the electric field inside the conductor now. For this value to be 0, E must be 0 now here. This E must be equal is the electric field inside a conductor. So from this what I can say now, tell me. From this what I can say now here. What is the electric field? What is the electric field inside my conductor? बोलिए सब बोलना पड़ेगा, जोर से बोल. What is the electric field inside a conductor? Must be what you tell me? 0. Anna बोलिए, tell me. This is the most important point, so everybody has to remember this thing. The net electric field inside the conductor is what? You tell me how much it is? 0. Is this point clear? Tell me. The net electric field inside a conductor is 0. And the net charge, not the net charge inside a conductor is how much? You tell me, which is also 0. So here what is the electric field inside a conductor? Tell me, which must be 0. Yes. So this is electric field must be inside a conductor is always it should be 0. Now as we know the Maxwell's first equation, what is the del dot E? We are applying inside a conductor. Del dot E, which is given as rho V by epsilon. E0 means this value 0. So which we can say rho V by epsilon equal to 0. That means how much is rho V must be? 0. So what is the net charge inside a conductor? You tell me. The net charge inside a conductor, which is equal to 0. And of course here we are talking about what type of conductors? You tell me. Conductors with sources or conductors without sources? Conductors with sources we are talking, or conductor without sources we are talking here? We are talking about what? You tell me now here, not this type of conductor. These are called as a conductors with sources. I am talking about the conductor when there is no sources. Let us say, we have taken some iron rod we have taken now here, iron. So any metal we have taken, that type of conductors we are talking. But here in the wires there is a flow of current is there now. So we are not talking about that conductor here. I am talking about the, if I not given any supply, what's going to happen? That type of conductors we are talking here. Now but there is, when we apply the voltage to conductor, there is, we have electric field inside a conductor, keep in mind. So when we don't given any electric field, then only it is 0. Fine, all of you? Done. Next one. The conductor does not allow any charge to enter into it. Conductor is a type of material, you know, these fellows are very selfish nature. Again, let us consider we have taken some this random conductor we have taken. See, is a completely, we are talking about, always remember, isolated conductor. What type of conductor you tell me? Isolated conductors only I am talking in this entire our discussion. All of you ध्यान से सुनिए. This isolated conductor, agar let us consider on this surface, let us consider I have placed some charge, I have placed on the surface. On the surface. Now I want to verify whether the charge will enter inside the conductor or does not enter into the conductor. I want to verify this thing. Suniye all of you dhyan se. Look at now here. So we have, when you place some charge Q, let us say some part of the charge is entered inside a conductor. Let us consider some part of charge is entered, Q part is entered. Let us see this thing. If I have the Q, this part of charge is entered into the conducting material, means what's going to happen, you tell me? Because of the charge, electric field we have or not? Because of the charge we have a electric field is there na? That is electric field E, which is given as KQ by R square. Hana boliye. Because the charge which is entered into the conductor, because of this fellow, it will create some electric field. If it is creating the electric field, then the charges will experience a force. Then because of the force, then what happens now, tell me? Because of the force, the charges will displace. If the charges are displacing, That means there will be a flow of current na? Then we have a flow of current. Now you tell me now here, in this conductor do we have any flow of current? Here do we have any flow of current or not, you tell me? In this conductor do we have any flow of current? There is no flow of current. There is no flow of, it is an isolated conductor now. We are not giving any energy. That means there is no flow of current means, so current should be zero, means there is no displacement. No displacement for 0. For 0 means electric field is 0. Electric field 0 means this value 0 means what is a possibility here? K is a constant which is non-zero. What's the possibility now here? Q must be only 0 now, tell me. Only possibility Q must be 0. That means we have assumed that some charge is entered into conductor, but how much the charge we have proved, you tell me, which we have proved this as a 0. That means what we can say here, the amount of charge which is entered into the conductor is completely 0. That means there is no charge is entering into the conductor. If there is no charge is entering into the conductor, that means where the charge will lie? The charge will lies completely on the surface of the conductor. Completely lies on the outer surface of a conductor only. The charge completely lie on the outer surface of the conductor. It cannot enter into the conductor. If any extra charge is placed on the surface of a isolated conductor, the extra charge distributes itself in such a way that the net electric field inside a conductor is hamesha 0. So there is no charge can enter into the, no charge can penetrate into the conductor. Is this point clear to all of you? Done. Next one. And you see this thing here, the another thing here. So the electric field at any point on the surface of the conductor is what you tell me? Normal. Normal to what you tell me? Conductor surface. The electric field at any point on the surface of the conductor is what direction? It is a normal to the conductor surface. Means what you tell me? Means what now here? Consider we have taken some conductor. This is a conductor. Right. Now let us consider here. So this direction is called as a tangential direction. This is called as what direction? Tangential. And this direction is called as normal. Normal means perpendicular. Now let us consider here. We have the electric field is consider some angle we have considered. This electric field is making some angle to this conductor surface, consider. Let us say here this electric field which we can resolve into two components now. This is one component and this is another component. Now what I should call this component to tell me? This is a component. How is component it is now, tell me? Tangential. Now here which I am calling this as E tan, I am calling this is the tangential component of electric field, and this is what I can say here, I am calling this as a normal component. Right. So now here, if the electric field is tangential, you see this thing here. Now in this conductor here we have charges present or not? Here we are talking inside part now here. Now you see this thing here, because of this tangential electric field, the charges inside the conductor will experience a force or not? Will experience a force. All of you tell me. This is what type of conductor? Isolated conductor. The charges will experience some force. Means what we can say now here, because of the force of the charges will displace, then we have a current we have. But lekin this is my isolated conductor. In this isolated conductor, do we have any flow of current will takes place? There is flow of current. What we have, there is no flow of current. If there is no flow of current, means what now here, there is no tangential force now here. This direction we should not have any force. Means for that this E tan must be equal to 0 now. So that means E tan must be equal to 0. So what I can say now here, the tangential components of electric field on the surface of the conductor must be 0. If not, what happens? If it is non-zero, see what happens, you tell me. Because of this E tan, the charges inside the conductor will experience some force. The charges inside the conductor will experience some force. Hana boliye. Because of the forces we have a current is there, but there is no current since it is a isolated conductor. So that means what I can say now here, we should not have any E tan, and if we have a E normal, maybe non-zero. If this electric field is non-zero, the charges will be on the surface only. Now they will come to this direction. There is no problem now here, tell me. So that's why the electric field can never be a tangential direction. It may be normal, but never be a tangential directions. Fine, all of you. And the last important point is, the conductor is an equipotential surface. How the conductor is a equipotential surface means what, you tell me. If you have taken one spherical conductor for easy understanding purpose, let us say this radius of the sphere, it is a solid sphere. The radius of the sphere is some capital R, right? This is the solid sphere we have taken. Now if we ask, so here at this location, if it is at a distance of R, what is the electric field at this point here? Electric field at this point. Potential, you tell me what should be given as, which we can say this is K. Let us say charge is Q. K Q by R. This is the potential inside the sphere. Now if you see carefully, this is the point A. If I say this is the potential at A, if I take the point B here, what is the potential at B, tell me, which is also given as, this is KQ by RA, and this distance which we can say KQ by RB. Now what is the potential on the surface, you tell me? Potential on the surface which is given as KQ by capital R. KQ by what, you tell me? Capital R. Capital R is a radius of the sphere, right? Now you tell me now here. Now you tell me. So in these cases, so KQ by capital R we have. Now from this what I can say, tell me now here. From this what we can conclude now here, if you see carefully, yes, conductor is a, so here there is no potential difference now. So at every point potential must be same. That means what I can say here, for that purpose this VA must be equal to VB must be equal to V surface होना पड़ेगा ना, बोलिए. So that's why the potential at any point inside the sphere which is same as the surface potential. Right. So why the charges does not experience now here? Look at now here. So all of you देखो इधर. This is my conductor. This is what you tell me. This is my conductor. Now you see this thing. This is a tangential direction and this is a normal directions. Now you tell me now here, if we have a forces like this, if you have forces like this, charges will move these directions. If I have forces like this, charges will move like this. And if I have forces like this upward direction, that means then what happens now? The charges will come to the top layer of a surface and they will hold there only. Charges, because of this forces, the charges will come to the top layer, they will stay there only now. The charges will come to the top layer, they will stay there only. That means what now here? We don't have any flow now here. If the charges are here this direction only, we have flow is happens, then only we have current. But if the charges are moving this direction, so there is no flow of current now, then we don't have any problem at all, right? That's a reason. So that means what we can say now here, the potential at any point on the surface of the conductor is same as the surface potential. Now this thing we can finally, you can remember this thing as like this. Let us say this is my conducting sphere. This is my conducting sphere. The radius of the sphere is capital R. Now I want to find the potential at this point. Potential at this point we are finding this, and this point is a. The point inside we are finding here. This point we are finding. This is at a distance of r. Now I want to find the potential at this point. This distance which is equal to, this is distance r. This point is A I am calling, and this point is B. I want the potential. See this thing. Listen carefully what we can do. The potential formula which is given as, what we can say here, charge is Q, which is given as KQ by, so denominator it may be a small r hoga, capital R hoga, we have a confusions. Yes or no? What we can do here simply, now you see this thing, I want to find the potential at the point A. If I want to find the potential at the point A, then what you do is, now you compare, now you can compare the radius of the sphere distance. So that means distance is this much, radius of the sphere is this much. Is दोनों में which is bigger value, tell me? I want to find the potential at this point. In this smaller and capital, which is the bigger value, tell me? If I apply this thing here, what is the bigger value, tell me? Which is the bigger value, tell me now here. So at this length is r, this length is small r, and this length is capital R. I want to find the potential at this point A. So which is bigger value? Radius is bigger or distance is bigger for at point A case? For the point A, which is a bigger value? Radius is bigger or radius of the sphere is bigger value, distance is bigger? Radius is bigger now. So take the bigger value simply. This is the potential if a point lies between 0 less than r less than capital R. That means 0 to capital R. That is inside the sphere. If I want to find the potential which is greater than capital R, now you tell me now at this point B I want. Tell me now potential. That is KQ by. Now for the point B case, which is a bigger value, small r is bigger, capital R is bigger. For the point B, which is a bigger value, small r or capital R is bigger. For the point B, which is a bigger value, I am asking, small r is bigger or capital R is bigger? For the point B case here, you tell me, for the point B case, radius is bigger, distance is bigger. Radius is bigger, distance is bigger. For the point B I am asking. For the point B case, which is a bigger value? Radius is bigger, distance is bigger. Smaller is bigger, then take the smaller, that's all. इसमें कोई खास बात नहीं है इसमें. KQ by whichever is bigger, you compare the radius and the distance. You can compare radius of the corresponding sphere and distance of the sphere. You compare whichever is a bigger, that is taken simply. Then all of you, whichever is bigger, that has to be taken simply, nothing else. Is this point clear to all of you? Then yes, fine. Right, so that's for the today's class, and all of you do revise all the things today, and tomorrow we'll meet at the same time. Tomorrow we'll meet at the same time. We'll meet 9 o'clock. Tomorrow we have a class. Okay then, and all of you do revise. If you have any queries and all, let me know. We'll discuss tomorrow. Fine, all of you. Okay then, see you. Bye bye. Good night.